Hi, I'm Jiayuan Gu, and I will present weekly supervised 3D shape completion in the wild. Our goal is to predict a complete shape given a real-world sparse partial point cloud. Previous shape completion methods require ground truth shapes from synthetic data and assume the input partial point cloud is aligned and normalized to a canonical frame. These methods do not transfer well to real data since both these conditions are not available. On the other hand, there are an increasing number of large-scale 3D datasets. Can we leverage these datasets to train 3D shape completion without ground truth annotations? Our key insight is that multiple views of a single object correspond to the same complete shape. And the complete shape can induce different views by projection. Thus, by leveraging multi-view consistency, it is possible to learn shape completion without ground truth shape and pose supervision. Similar ideas have been explored in 3D reconstruction from single images. DBC trains a convolutional network to predict both the shape and the pose from a single image by minimizing the projection error. Given several views of an object, the projections of the predicted shapes to the predicted camera poses should match the provided views. Since 3D point clouds can be lifted from depth images or random images, DBC serves as a good baseline. Therefore, we propose a general and a realistic setting, weekly supervised 3D shape completion, where we have access to a set of unaligned and partial real-world observations of objects. Note that the complete shape of a partial observation is defined by the canonical shape and the pose. The key challenge is how we can learn the canonical shape and the pose when we do not have access to the ground truth for either. To tackle it, we jointly learn the canonical shape and the pose of the object. Let's have a closer look at our method. First, given two partial point clouds, we predict their canonical shapes and poses. Then, we transform the canonical shape predicted from one input to two complete shapes according to predicted poses. We use an asymmetric chamfer distance to force the output canonical shape to completely cover the input observation. Moreover, using our knowledge of how the sensor acquires observations, we can simulate which points on the surface are observed based on the estimated complete shape and the estimated pose. We can then force the generated point cloud to match the true observation. We also introduce a simple, flexible, and efficient way to infer the surface points. Let's summarize our method. During training, given multiple partial point clouds of the same object, our model learns to predict complete shape and pose matching each view. During inference, our model can be applied to a single partial point cloud. Thus, our model can work as fully supervised method during inference, while it requires less supervision during training. Additionally, our method can be easily extended to challenge partial point cloud registration. Point cloud registration is the process of finding a spatial transformation that aligns two point clouds. Given two point clouds, our model can predict their poses and induce the relative pose to align them. For experiments, we compare our method with several baselines on both synthetic and real datasets. For real datasets, we fuse partial point clouds of multiple frames to obtain ground truths. To verify our implementation, we compare with DPC on the synthetic dataset ShapeNet. Our method outperforms DPC quantitatively and shows reasonable visual results. DPC has several limitations when applied to real data. For example, it is assumed that canonical shapes are normalized into a unit cube, and the camera distance to the object is fixed. Thus, we adapt DPC to DPC LiDAR with several modifications. First, we replace perspective transformation with polar transformation. Second, we scale the predicted canonical shape with a fixed factor, namely 6 meters. Last, we add a radial offset according to the input point cloud and predict translations to the sensor. Despite modifications, DPC LiDAR suffers from sparse and unnormalized real data. Besides, we introduced two baselines based on ICP, where we fuse partial point clouds according to relative poses estimated by ICP algorithms. Compared to baselines, we show better shape completion results on in the wild real data. Since our method has knowledge of complete shape and poses, our extension to point cloud registration outperforms ICP baselines. Although without ground truth during training, our model learns to complete shapes of different sizes. According to estimated poses, we can also fuse partial point clouds from multiple frames. We can observe that the point cloud fused by our method is more accurate than by ICP baselines. Let's see more examples from different viewpoints. We can observe that our method is able to predict complete shapes close to ground truth with fewer outliers. It is also able to hallucinate points missed by ground truth. Compared with ICP baselines, our method estimates more accurate poses and thus generates better fused point clouds. Next, we demonstrate our 3D shape completion results on sequence of point clouds. Our method generates reasonable shapes and shows consistency across frames. Last but not least, our method also supports optimization during inference. We experiment on parked trunks of semantic kitty by fine-tuning the model pre-trained on our 3D vehicle dataset. Despite few instances to fine-tune, our method manages to adapt to unseen data, capture complete shapes, and estimate accurate poses. To summarize, we propose a weakly supervised approach to learn 3D shape completion from unaligned partial real-world point clouds without pre-training. Our promising results show that it is feasible to learn 3D shape completion from large-scale 3D data without shape and pose supervision. Besides, the extension to partial point cloud registration implies that the knowledge of complete shape helps tackle the task. Although our method still requires instance-level information, it can be integrated into auto-labeling tools, given a 3D detector and tracker. Thanks for listening.